welcome to this module which is pertaining to the source model for various gases. Now have a look about that what we have studied previously. We have introduced that various aspect of source modeling. We have discussed about the step to follow starting from release incident to selection of model depending upon the type and the nature of various incidents, mitigation and the consequences analysis. We have discussed about the basic source models like flow of liquid through a hole, flow of liquid through a hole in a tank and flow of liquids through pipe. Now in this particular module we are going to discuss about what is the understanding aspect, the difference between the handling of liquid and vapor, type of flow of vapor through hole and pipes, flow of vapors through different type of holes, flow of gases through pipe and their types, flashing liquids, liquid pool evaporation or boiling. Now what we need in different models for gases, now usually gases are compressible fluids and hence all of its physical properties changes according to the external conditions. These external conditions may be pressure, maybe temperature, etc. Moreover, handling of gases can be more tougher than liquid. Now, because of the variety of reasons, because one reason is the gases they are usually invisible, hence a small leakage is difficult to detect unless otherwise you are able to recognize through its odor. Vapors at same temperature, due to the presence of latent heat, they are more energetic than liquid. Now here we have a comparison of liquid versus vapor. Liquid usually they are compressible flow, whereas vapors they are the compressible one. In liquids the kinetic energy term is negligible, whereas in vapors the pressure energy converts to kinetic energy. In the liquids approximately constant density, however the vapors the temperature, pressure, density all changes when it passes through a narrow opening. So you can imagine that how critical is the scenario for the modeling in vapors. Now physical properties of vapors can be assumed constant for small changes in pressure like P1, P2, P3 or etc. and at very low velocities. Now let us have a look about the types of flow of vapor through holes and pipe. Now there are two type of things, one is throttling, another one is the free expansion release. Now throttling we all know maybe through a small cracks, there is a large frictional losses, a little conversion of pressure energy to kinetic energy. They require the detailed information on the physical structure of the leak. So you must have all these type of things with you while you are considering the throttling behavior. Whereas in free expansion, the most of the pressure energy converted into kinetic energy. Assumptions to isentropic process is usually valid because while you consider this free expansion you may have to take certain assumptions. So one assumption is to the isentropic process which is usually valid in this case. Now they require only a diameter of a leak, so this is a bit easier. Now there are two type of things which we need to consider under the head of the free expansion. One is the non-choked or subsonic, another one is the choked or sonic one. So while considering the throttling flow, throttling is a type of flow such as a flow through valve, like in this figure you can see the flow through a valve or a crack or within the porous material. So these geometries pose high resistance to flow that results to a large amount of pressure drop. Now you can see in these figures this is the partially open valve and you can see the throttling flow, whereas in the second figure you can see this is a porous plug and you can see the flow is through this porous plug under the throttling behavior. So while considering the throttling flow, we can seek the help of first law of thermodynamics. Now first law of thermodynamics is dE over dt is summation mass flow rate Ws plus EP plus EK in minus summation M out H plus EP plus EK out. Now here E is the total energy and hence dE over dt represents rate of change of total energy. Ws is the shaft work and this dot over this represents the quantity per unit time. M represents the mass flow rate of the liquid. In case, mass flow rate of fluid. Now here fluid is gas. H is enthalpy of the gas. EP and EK are the potential and kinetic energy at inlet and outlet. So we may take different assumptions for this particular equation, like the potential and kinetic energy effects are neglected. We may assume the steady flow, adiabatic conditions, and we may assume the shaft work is 0. So by implying these assumptions in our system, we can get this equation dE over dt is equal to Ws, which is cut because we have assumed the shaft work negligible, then summation Mi H plus EP plus EK in. Now this is again cancelled out, then M out H plus EP plus EK for the outlet. Now again this is cancel out. So hence isenthalpic flow can be considered in this particular case. So if we take that dt is a function of P and H, then we can take the partial derivative like this: dt is equal to del T over del P at H dP plus del T over del P at constant P dH. Now define the Joule-Thomson coefficient. This is the Joule-Thomson coefficient. Now mu is equal to del T over del P at constant H. So if we consider the isenthalpic flow, then in that particular case del T over del H at constant P is equal to 0, and if we integrate, then the T out minus T in is equal to integration of inlet to outlet mu dP. Now the most gases have positive Joule-Thomson coefficient, so as the pressure drops, the temperature drops. Now let us have a look about a free expansion leak. Now here you can visualize this figure. You are having a gas pressurized within a process unit and it leaks through this particular point. So initial condition, if we say that P naught, T naught, U naught is equal to 0, delta Z is equal to 0, and shaft work is equal to 0. And here the things are at the external surrounding. So here you can have a throat where P upon U is less than the sonic velocity. So if we consider this particular aspect through whole, then we can write the mechanical energy balance for flow, and that is the integration delta P upon rho plus delta RU square 2 alpha GC plus F is equal to 0, where delta P over delta rho is the pressure energy change, P is the pressure of the fluid, rho is the density of the fluid, bar U is the average velocity at the hole. So we need to define the discharge coefficient C1 at this juncture. Now this is defined as delta P upon rho minus F is equal to C1 square minus integration of delta P upon rho. So, but if at this point of time we can define the discharge coefficient. Now C1 is the discharge coefficient. Now if we combine both the equation and integration from integrate from P is equal to P naught V is equal to 0 to P is equal to P, then we will have C1 square P naught to P delta P upon rho plus bar U square upon 2 alpha GC is equal to 0. So for any ideal gas undergoing isentropic expansion, we are having this universal equation, PV to the power gamma is equal to P upon rho to the power gamma is constant. This is the well known thermodynamic equation. So velocity of a fluid at any point during the isentropic expansion is given by bar U square to GC C naught square gamma. Gamma is the adiabatic constant. And usually it is represented by Cp over Cv. So bar U square is equal to 2 GC C naught square gamma upon gamma minus 1 P naught upon P 1 minus P upon P naught gamma upon gamma minus 1. Now therefore the mass flow rate of any time during the isentropic expansion can be given by Qm is equal to C naught A is the area of cross section, P naught 2 GCm upon Rg T naught gamma upon gamma minus 1 P upon P naught 2 to the power gamma minus P upon P naught gamma upon gamma minus 1. So by this way you can calculate the mass flow rate at any time during the isentropic expansion. So this is the general equation. Now sometimes velocity of a gas increases with a decrease in downstream pressure or increase in upstream pressure until it reaches a critical velocity. The choked pressure P choked is the maximum downstream pressure resulting in maximum flow through the hole or a pipe. So if we wish to calculate the P choked, then it is represented as P choked upon P is equal to 2 upon gamma plus 1 gamma upon gamma minus 1. To be more precise, you can get this particular P choked from this particular equation. Now, for if we have P is less than P choked, the velocity of the fluid at throat is equal to the velocity of sound. Velocity of the fluid at the throat is equal to velocity of sound, and the velocity and mass flow rate cannot be increased further. And third point is that the flow become independent of the downstream condition. So this type of a flow is called choked, critical or sonic flow. Now in the next aspect we will consider the flow of gas through pipe. Flow of gases through pipes. Now here we are having a pipe like this. Here the initial conditions are P1, T1, U1, Ma1 and Q is equal to 0. Here the final condition are P2 is less than P1, P2 is the greater than P1. These two are the conditions. T2, U2 is greater than U1 or U2 is less than sonic velocity. Ma2 is greater than Ma1 and Ma2 is less than 1. Now Ma is the Mach number. Here Ma is the Mach number. So Ma is represented as Ma upon bar U. Ma is equal to bar U upon A. Now A is the velocity of sound. So A is represented as integration Gc del P over del rho at S. So for ideal gas, A is equal to gamma Gc Rgt over m. So by this way you can calculate the velocity of a sound. So velocity of a gas, if you wish, of gas is represented as bar U is equal to A, that is the speed of sound, is equal to gamma Gc Rgt over m. So the mass flow rate at the choked condition would be Qm, that is choked, is equal to C naught A P naught gamma Gcm upon Rgt naught 2 upon gamma plus 1 upon gamma minus 1. Now C naught is equal to 0.61 for sharp edged orifice and C naught is equal to 1 for worst case scenario. So these are the two conditions which may need to encounter during the course of calculation. Now there are two types of flow. One is the adiabatic flow, and second one is the isothermal flow. Now in adiabatic flow, the well insulated wall, there is no energy loss to the surrounding, and in isothermal flow the constant wall temperature, that is the submerged pipe. So let us take the example of adiabatic flow. Now please recall the previous figure which we have, and for the convenience I am redrawing it. That was the pipe flow. Initial conditions were fixed at P1, T1, U1, Ma1, and the final conditions are P2 is less than P1, P2 is greater than P1, and so on and so on. You may recall the previous figure. Now, as shown in the figure, the gas is flowing from left to right direction due to the presence of a pressure gradient across the two ends of the pipe. Now, as the gas moves forward, it starts expanding due to the decrease in the pressure, because P2 is less than P1 in the direction of the flow. This results to increase in velocity and the kinetic energy of gas. The increase in kinetic energy is compensated from the decrease in thermal energy of the gas. Now, the gas starts cooling down due to the decrease in thermal energy. So, the friction force between the gas molecules and the wall of container also plays a significant role in the change in temperature of the gas as well as towards the pressure drop. Now, these frictional forces increase the temperature of the gas. Hence, both cooling or heating of the gas during the flow is possible. So, through this way, we can write the mechanical energy balance equation delta P upon rho plus bar U du bar upon alpha Gc plus G upon Gc dz plus df is equal to Ws upon m. Now, the following assumption, that is G upon Gc dz, is valid for this particular case. So, assuming the straight pipe without any valve or fitting, although this is purely an assumption, so we will have df is equal to 2f bar u square upon dl Gc d. Now, this is for the straight pipe without any valve or fitting and no mechanical leakage. So, this is again the purely assumption that if no mechanical leakage are present, then delta Ws is also equal to 0. So, we may write the total energy balance equation like this: dH plus u bar u du bar upon alpha Gc plus G upon Gc dz is equal to delta Q minus this. This is the total energy balance equation. So, if we go ahead further, then this is represented by gamma plus 1 upon gamma ln P1 T2 P2 T1 minus gamma minus 1 to gamma P1 square T2 square minus P2 square T1 square upon T2 minus T1 1 upon P1 square T2 minus P2 square T1 plus 4FL upon D is equal to 0. Now, let us take the G, which is a mass flux is equal to 2 GCM upon RG, gamma upon gamma minus 1, T2 minus T1, T1 upon P1 square upon T2 upon P2 square. This is the mass flux. Now, in the other example, we may take the isothermal flow. Again, considering the figure of the pipe flow, P1, U1, MA1, P2 is less than P1, P2 is greater than P choked, U2 is greater than U1, U2 is less than sonic velocity ma2 ma1 or ma2 is less than 1. So if we consider this type of aspect, then the isothermal flow of a gas uh, we have considered in this case the T is constant. Let us have the thing that this we are considering the L length. Now considering the case when the velocity of the gas is well below the sonic velocity of the gas, like this. Now gas is flowing from left to right direction due to the presence of pressure gradient across the two ends of the pipe. These are the two ends of the pipe. Now gas starts expanding due to the decrease in pressure in the direction of flow. Now as the gas expands, the velocity must increase to maintain the same mass flow rate. So the pressure at the end of the pipe is equal to the pressure of the surrounding. So the temperature is constant across the entire pipe length. We have already taken this assumption. So we may write the mechanical energy balance equation that is delta P upon rho plus bar U du bar U upon alpha Gc plus G upon Gc dz plus df is equal to. Now we may take the following assumption for this particular case, that is G upon Gc dz is almost equal to 0. Now we may assume that the straight pipe without any valve or a fitting, so df is equal to 2f bar u square dl upon gcd. This is for the straight pipe without any valve or fitting. So if there is no mechanic leakage, then this is equal to 0. So we may use the following conditions. T2 is equal to T1 because we have assumed the isothermal condition. Then P2 upon P1 Ma1 upon Ma2. Now G is equal to rho U Ma1 P1 gamma GCM upon RGT, or 2 ln P1 upon P2 minus GCM upon G square RGT P1 square minus P2 square plus 4 FL D is equal to 0, or 2 ln Ma2 upon Ma1 minus 1 upon gamma 1 upon Ma1 square minus 2 square plus 4 FL D is equal to 0. So by this way we can model or we can calculate the appropriate things. Now there are certain conditions related to the flashing of liquid, and we may consider the 4 cases: the adiabatic flashing, flashing of flashing liquids. So first thing is that we may assume the adiabatic flashing. Second is adiabatic flashing through hole. Third is isothermal flashing through hole, and fourth is the liquid pool boiling. So flashing liquids. Now flashing event may occur when the liquid is stored under the pressure above their normal boiling points. Now if liquid is stored in a container or flowing in a pipe develops a leak under such condition, the liquid starts partially flashing into vapor. Explosive flashing may also occur. So this process can be assumed as an adiabatic process. The energy of vaporization comes from the superheated liquid, which results to the decrease in temperature of the liquid. Now, if m is the mass of original liquid, and Cp is the heat capacity of the liquid, energy plus mass degree, and T naught is the temperature of the liquid before depressurization, temperature of the liquid before depressurization. Tb is the depressurized boiling point of the liquid. So excess energy contained in the superheated liquid may be calculated by this original thermodynamic equation. Q is equal to mCp dt. This excess energy provides the heat of vaporization delta HV for the mass of liquid vaporized, that is dmV. This is the mass of liquid vaporized, and this is the heat of vaporization. So dmV is equal to Q upon delta HV mCp dt delta HV. So we can calculate the fraction of liquid vaporized like Fv is equal to dmV upon m Cp dt upon delta HV. Now, if we integrate between the initial temperature T naught with the liquid mass m and the final boiling point Tb with liquid mass m minus mv. So, if we integrate between this, then m integration between m to mv dmv upon m is equal to T naught Tb Cp dt upon delta HV. Now, ln m minus mv upon m is equal to minus Cp T naught minus Tb upon delta HV bar. So, Fv is equal to m minus mv upon m is equal to 1 minus mv upon m. So, after substituting the value, we get the fraction of liquid vaporized as Fv is equal to 1 minus exponential of minus Cp T naught minus Tb upon delta HV bar. Now, equilibrium flashing choking conditions. So, fluid path is fluid path length greater than 10 centimeter. Now, choked pressure is approximately assumed equal to the saturation vapor pressure of the fluid in question. So, another aspect is that the liquid is stored above saturation pressure. If we take liquid is stored above saturation temperature. So, if L is less than 10 centimeter, assume incompressible liquid is flowing. Now, if L is greater than 10 centimeter, assume choked flow with P is equal to P saturation. So, like this, here the P1, this is the length L, and this is the P2. So, this is the case of adiabatic flashing through holes. So, mass flow rate can be given as Qm is equal to AC naught to rho 1 Gc P minus P saturation. So, this gives you the mass flow rate, where A is area of release, C naught is the discharge coefficient, which is unitless, rho 1 is the density of liquid mass per volume, P is the pressure within tank, and P saturation is the saturation pressure. Now, let us consider the isothermal flashing through a hole. Now, if we assume the choked flow of a two-phase fluid, then Qm is equal to A upon minus Gc dV over dP. This is the isothermal flashing hole. Now, here V is the specific volume, V is equal to VFG FV plus VF. VFG is the difference in specific volume, VF is the liquid specific volume, FV is the mass fraction of vapor. Now, if we differentiate with respect to pressure, then we will get dV over dP is equal to VFG dFV upon dP. So, we derived that dmV upon m is equal to Cp dt delta HV, and dmV is equal to minus dm1. So, applying all these conditions, we have, and therefore, dmV upon m is equal to minus Cp dt delta HV is equal to dFV. Now, if we substitute dF in this particular thing into dV dP, we have dV over dP is equal to minus V Fg Cp L dt delta HV dP. So, the Clausius-Clapeyron equation can be used for dt over dP. So, dP over dt is equal to delta HV upon T V F G. So, if we combine the equations, then we will get dV over dP is equal to minus V square Fg Cp L T delta HV square. So, we can substitute into the final relationship, that is Qm minus Gc upon minus V square Vfg square Cpl T upon delta HV square. Now, reducing the equation for vapor mass flow rate, then Qm bar is equal to delta HVA VFG GC CPL T. So when flashing process is done done at or near P saturation, small droplets of liquid are also entrained with vapor. So design assumption is taken as the mass of the liquid entrained is equal to the mass of vapor formed from the from flashing. So in this particular module, we have discussed the different aspect of leakage through hole and orifice, and in the subsequent module we will discuss the liquid pool evaporation and other models for applicable for gaseous flow. Thank you.